My name is Dale Cortez, and in this segment, we are doing a deep dive code review of the end-to-end Python pipeline I engineered to analyze housing affordability across Florida's 67 counties. To set the stage, housing cost burden is a critical metric defined by HUD. If a household spends more than 30% of its gross income on housing, it's considered burdened. If it crosses 50%, it's severely burdened. As a Florida resident and University of Florida alumnus, I wanted to programmatically parse the raw public records provided by the UF Shimberg Center for Housing Studies to look at structural trends. Specifically, I wanted to answer 7 core business questions. Question 1, volume and rate. Which counties face the absolute highest burden by raw count and rate? Question 2, tenure split. How does the burden profile shift between renters and homeowners? Question 3, income stratification. Which area median income AMI bands are entirely priced out? Question 4, regional benchmarking. How does my home region, Manatee, Sarasota, Pinellas, and Hillsborough, compare to the statewide unweighted average? Question 5, historical trends. Is homeownership in my home area rising or falling over a 35-year timeline? Question 6, wage alignment. Can a local single median wage cover HUD's fair market rent for a standard 2-bedroom? Question 7, demographic impact. Which specific family types, such as single mothers, are carrying the highest burden? Let's step directly into the pipeline execution. We start by importing our standard stack: NumPy, Pandas, Matplotlib, Seaborn, and Plotly. I've isolated my local market area into a reusable list, constant named home area for downstream filtering. The raw data arrives as a multi-sheet Excel workbook. In cell 2, you can see that the raw spreadsheet contains descriptive headers in the first 3 rows rather than structured data. To handle this, I use a non-header ingestion in cell 3 and programmatically slice the data frame using .iloc from index 3 onwards to drop the fluff, explicitly assigning clean relational column names: county, income band, not burdened, mod burdened, and severe burdened. Cell 4 highlights a critical step where data engineering directly impacts analytical accuracy. During my data auditing phase, I discovered that for several small rural counties, the Shimberg Center leaves cells completely blank where the household count is too small to safely report. Pandas naturally reads these blanks as NaN values. Because NaN is contagious in Pandas arithmetic, any addition operation like NaN plus values results in NaN. Left unchecked, a single blank cell would cause an entire county's household route to drop silently during a group-by-sum rollout. This structural bug skewing data actually inflated some rural counties' calculated burden rates by 15 to 30 percentage points. To protect data integrity, I run a systematic fill-naze zero check on the numeric columns. I then derive 2 engineered features using vectorized Pandas operations: cost burdened, the sum of moderate and severe burden, and total household, the sum of all households in that band. In cell 5, I call data frame describe to generate a quick statistical summary, verifying the distribution spreads of these newly engineered metrics before changing the shape of the data. With clean data frames, cell 6 performs a data rollup using group by county and aggregates our counts using sum. I call reset index immediately to flatten the index, pulling the county attribute out of the index state and back into a queryable column format. I calculate the overall burden rate as a vectorized percentage, cost burdened, divided by total household times 100, rounded to 1 decimal place. To prepare this dataset for spatial visualization without manually mapping strings, cell 7 acts as our bridge to GIS. I read in a standardized Federal Information Processing Standards FIPS lookup table for Florida's 67 counties and execute a relational inner join using Pandas merge county and Federal Information Processing Standards on county. This ensures every row carries a precise 5-digit string identifier required for choropleth mapping geometries. I pull a quick subset in cell 8 just to verify our home counties look correct, and then in cell 9, we cast the burden rates into a native NumPy array to analyze the distribution shapes. The unweighted mean across all 67 typical counties is 26.8%, while the median sits tightly at 25.9%. Demonstrating a relatively balanced distribution before factoring in total population weights. For static reporting, cells 10 and 11 drive the Matplotlib rendering engine. For the top 10 counties chart, I use a list comprehension and F-string formatting to convert raw floats into clean, comma-separated integer labels, passing them straight into plot bar label. Cell 11 plots our distribution histogram, where I manually draw an unweighted vertical reference line at the county mean using plot AX-V line. Cell 12 leverages Seaborn to evaluate our income bands. I pivot the data frame to map counties against the 5 core AMI brackets, applying the yellow, orange, red color palette. The visual matrix immediately exposes that cost burden isn't evenly distributed. It is heavily concentrated at the bottom of the income scale, where over 80% of households earning 30% AMI or less are actively cost burdened. To put this in real economic terms, Cell 13 parses Sheet 5 of the workbook to pull actual American Community Survey median household incomes. In Manatee County, the median income sits around $81,400, meaning our highest burden bracket represents families living on $24,400 or less per year. Crucially, this table highlights a stark wealth gap. Across our entire region, renters earn roughly half to two-thirds of what homeowners bring in. This income variance leads directly to the tenure analysis in Cell 14. By passing our long-form aggregated renter and owner data frames into a single Seaborn bar plot and configuring the hue parameter as the housing tenure, we expose a massive structural divide. Across our home region, Manatee, Sarasota, Pinellas, and Hillsborough, the cost burden rate for renters hovers right around 50%. Meanwhile, the homeowner burden rate stays well below 25%. This visual matrix proves that housing volatility in Florida is heavily concentrated in the renter market. This answers our second core business question. The burden profile shifts dramatically and systematically against those who do not own their homes. To present these findings to stakeholders in a digestible format, cells 15 through 17 bridge our tabular data into interactive GIS mapping and trend analysis. Utilizing Plotly graph objects, cell 15 maps the statewide burden rates using the yellow, orange, red color palette. Because we previously joined our structural data with Federal Information Processing Standards identifiers, the geometries link flawlessly. When you hover over the map, it dynamically exposes the raw volume of burdened households alongside the percentage rates, clearly flagging coastal hubs in South Florida as the absolute highest burden zones. Cell 16 applies this exact same logic to isolate the raw volume metrics for our local market area. Finally, moving to cell 17, we pull in historical data from sheet 4 to see if this renter squeeze matches a drop in home ownership. By applying the .T transpose operator to pivot our years onto the x-axis, the resulting line plot reveals remarkably stable home ownership rates over the past 35 years. This confirms our core analytical conclusion. This structural housing crisis isn't driven by a massive inventory shift in who owns a home, but rather a localized price crisis targeting renters and owners. And next, we transition from geographical areas to wage realities and household vulnerability in cells 18 through 20. In cell 18, we compare median local hourly wages against the 2025 HUD fair market rent of $1,846 a month for our specific metropolitan statistical area. The resulting bar plot reveals a stark reality. Any occupation colored in red represents a single median wage earner who is automatically cost burdened trying to afford a standard two-bedroom unit. Essential workers like paramedics, firefighters, and elementary school teachers are spending well over 30% of their income on rent. To understand who is bearing the brunt of this pressure, cells 19 and 20 split the data by household types. The Seaborn heat map in cell 19 clearly demonstrates that single-parent homes and non-family households carry the heaviest burden. Finally, in cell 20, we zoom in specifically on single-mother households who rent. This reveals our most vulnerable segment of all, with an alarming 54% to 62% of single-mother renter families living in active cost burden across our home counties. Our final step brings us to cell 21, which acts as our programmatic executive summary. Instead of hard-coding static bullet points, every single metric shown here is parsed live from our upstream data frames to definitively answer all 7 core business questions. The console printout beautifully consolidates our entire story, from Miami-Dade ranking as the state's highest burden hub to our local renter-to-owner wealth gap, all the way down to our demographic splits. It officially flags that single-mother renter families face the steepest regional climb, with up to 62% living in active cost burden. Ultimately, the pipeline proves that across Florida's 67 counties, a staggering 3,045,514 households are actively cost-burdened, wrapping up a completely automated end-to-end data engineering architecture. Before we wrap up, let's look at the limitations section of the notebook for a quick data audit reference. As data engineers, we must note that the Shimberg Center relies heavily on American Community Survey 5-year estimates, which introduces minor margins of error in rapidly growing counts. Furthermore, data suppression naturally occurs in small rural counties to protect privacy, which we successfully handled using our Fill-Nay Zero strategy. When presenting these findings, we also have to account for specific structural nuances, such as different time windows across data sheets, single earner household baselines, and the notable college town effect, which can artificially inflate burden rates in university counties like Alachua due to off-campus student populations. Ultimately, this project is descriptive, not causal. It maps out exactly where and who the data represents without trying to force a policy conclusion. This end-to-end Python pipeline effectively turns raw public records into actionable spatial and demographic business intelligence. Thank you for watching, and feel free to review the full repository in the links below.